Great. Yeah, welcome to the track A session on geometry and approximation. We have two talks in this session. The first talk is by Eklavya Sharma on approximation algorithms for multidimensional packing.
Thanks. Yeah, I'm Eklavya. I'm currently a student at University of Illinois at Urbana-Champaign. But when I did this work, I was a master's student at Indian Institute of Science, advised by Professor Arindam Khan. And this is a joint work with him and another student, KVN Srinivas at IISc. Okay. Yeah, so I'll start by talking about the geometric bin packing problem. In this problem, we are given in the two-dimensional geometric bin packing problem, we are given a set of rectangular items, and we are given an infinite supply of identical rectangular bins. And our task is to pack these items into the minimum number of bins. Yeah, so there are actually two. So in this talk, we'll focus on axis-aligned packing, which means that the edges of the items should be parallel to the edges of the bins. This is the only kind of packing that we'll allow. Okay, there are actually two versions of the problem. There's a version where we allow rotating the items by 90 degrees, and there's a version where we do not allow. Okay. So an application of this problem is in cutting sheets. So often raw material is available in large standard size sheets, and from those we want to cut out smaller rectangular pieces of desired sizes. So this is exactly the geometric bin packing problem. And here rotations are generally allowed. Another application is placing advertisements in a newspaper or on a website, and here rotations are not allowed. Okay. There's also a three-dimensional version of this problem where the items and the bins are cuboids. So the two-dimensional and the three-dimensional geometric bin packing problems are NP-complete and NP-hard. And in fact, it's NP-complete to check if a set of items can be packed into a single bin. And so we turn to approximation algorithms. And this result that it's NP-complete to check if items can be packed into a single bin means that we cannot get an approximation ratio better than 2. Okay? But this hardness result only holds when the optimal solution contains just one bin. But in practice, there are a large number of items, and so the number of bins is also large. So a question is that can we do better in that setting? Okay? And for this reason, we focus on a different notion, which we call asymptotic approximation. So we say that an algorithm A for bin packing is alpha asymptotic approximate. If for some constant beta, we have AI is at most alpha times opt I plus beta, where AI is the number of bins used by the algorithm A to pack the set I of items, and opt I is the minimum number of bins needed to pack I. Okay? And here alpha is called the asymptotic approximation ratio of the algorithm. So here's a list of some of the algorithms. So one of the first algorithms for this problem is called next fit decreasing height. It's a fast and efficient algorithm, and it has an asymptotic approximation ratio of 4. And since then, there's been a series of improvements, and currently the best known algorithm is by Nikhil Bansal and Arindam Khan, and it gets an asymptotic approximation ratio of around 1.405 plus epsilon. So these algorithms, this algorithm takes a parameter epsilon as input, and the asymptotic approximation ratio has epsilon in it, and the running time increases as we decrease epsilon. Now I'll talk about a different version of bin packing that's called vector bin packing. So let's suppose we have a set S of vectors, d-dimensional vectors, and each coordinate of each vector is a number between 0 and 1. And we say that such a set of vectors can be packed into a bin if we sum all of the vectors, and in the sum each coordinate is at most 1. Okay. So, and in the d-dimensional vector bin packing problem, our task is to partition these vectors such that each partition can be packed into a bin. Okay. So for two-dimensional vector bin packing, this is a way to visualize this problem. So these arrows here are items, and we want to partition these items such that in each partition, if we chain all of these arrows together, they all lie completely in a unit square. So an application of this problem is scheduling long-running jobs onto identical servers. So each server has requirements of how much RAM it needs, disk space, network bandwidth, etc. And every server has a certain amount of RAM, disk space, etc. So here are some of the known algorithms. One of the first algorithms had an asymptotic approximation ratio of d plus epsilon, where we're working on the d-dimensional vector bin packing problem. And then Bansal, Caprara, and Suridenko devised a technique called round and approx framework, and they combined that with Luecker and Vega's algorithm, and that gave us an asymptotic approximation ratio of 1 plus log d plus epsilon. And then Bansal, Khan, and Elias improved that further to 1 plus log of 1.5 plus epsilon for the special case where d equals 2. So I've talked about these two versions of bin packing, and now I'm going to talk about a variant that somehow combines these two problems, which we call the generalized multidimensional packing problem. So a motivating application is this, that let's say we have n cuboidal goods that need to be shipped using trucks, and each good has a weight associated with it, and each truck has a weight capacity. So here we have two kinds of constraints. We have a 3D geometric constraint, which means that the cuboid should actually fit into the truck, but that's not sufficient. We also need to ensure that the items don't, total weight of the items don't exceed the weight of the truck. Okay? So this problem generalizes the three-dimensional geometric bin packing problem. In fact, it's equivalent to that if all items have zero weight. And if we fix two of the geometric dimensions to be equal to 1, then this problem is exactly the same as two-dimensional vector bin packing. So we can actually generalize this further, and what the problem that we get is called DG DV bin packing. We have DG dimensional cuboids, and each cuboid has DV weights associated with it. And so we say that this problem has DG geometric dimensions and DV vector dimensions. And in the previous example that I talked about, DG was equal to 3 and DV was equal to 1. So this generalizes DG dimensional geometric bin packing and DV plus 1 dimensional vector bin packing. So this is a practical problem, and it has received a lot of attention from applied researchers, but so far there hasn't been much theoretical analysis of this problem. So we fill this gap. So we have a few contributions. First is that we give a few simple algorithms for this problem. We have two algorithms named simple pack and better simple pack. So they basically just use known algorithms for geometric and vector bin packing as black boxes, and the algorithms themselves are simple. It's just that they delegate their work to other state-of-the-art algorithms for these other two problems. Okay. Then we give a more sophisticated algorithm called the CB-pack algorithm, which is for is for 2, D bin packing. That means that rectangles with weights. Okay. And we do this by extending some of the state-of-the-art techniques used in 2D geometric bin packing. Yeah, and finally, there's a famous technique called the round and approx framework for bin packing. And we show that this technique can also be extended to the setting of DGDV bin packing. Okay. Well, okay, so here is a summary of the algorithms that we have. So there's not much to speak here, so I'll just wait for you to look at the slide for around 10 seconds. Any questions so far? All right, I'll proceed. So I'll talk about what the better simple pack algorithm is. Okay. So let's say we are given a set I of 2, D items, and so the first step of this algorithm is that we replace the geometric dimensions of the item by its area, and this gives us a d plus 1 dimensional vector bin packing instance, which I call I hat. So, and the next step is that we pack I hat into d plus 1 dimensional vector. We pack I hat into bins using a d plus 1 dimensional vector bin packing algorithm. And the next question is that can we somehow use this packing of I hat to get a packing of the original items I? So let there be m bins in this packing of I hat, and let j hat k be the d plus 1 dimensional vectors that get packed in the kth bin. Okay. And let jk be the corresponding original item. Okay, just because j hat k fits into a bin doesn't mean jk will also fit into a bin, but maybe we can fit jk into a small number of bins. So this is exactly what we do. For each k, we pack jk into bins using a two-dimensional geometric bin packing algorithm. Okay, so let's say these two bins are the d plus one-dimensional vector bin packing bins that we get, and for each such bin, we pack the geometric items using a geometric bin packing algorithm. So Steinberg gave an algorithm that gives us the guarantee that if the items have total area at most 1, then they can be packed into 3 bins. And these items do have total area at most 1 because that's how we constructed I hat. So suppose the vector bin packing algorithm that we used is alpha asymptotic approximate, then the total number of bins that we use is at most 3 alpha times opt of I hat. Okay, where opt means the minimum number of bins needed to pack an instance. And opt of I hat is at most opt of I, because by reducing the geometric dimensions to the area, we're only making the problem simpler. So this means that our algorithm is 3 alpha asymptotic approximate. And if we plug in specific vector bin packing algorithms, these are the approximation ratios that we get. Okay, so that was it for the better simple pack. Now I'll talk about the round and approx framework. So this is basically a technique of equipping existing algorithms with randomized rounding of a linear program called the configuration linear program. So I'll first define what a configuration means. So let's say we're given these 3 items, then a configuration means a subset of items that can be packed into a bin. So here are 4 different configurations that I've showed. So we can think of bin packing as the problem of deciding what configuration to use for each bin. Okay? So the problem can be equivalently stated as we must pick a set of configurations such that the number of configurations is minimized and each item appears in at least one configuration. Okay? And another way to think of it is that bin packing is a set cover problem where each configuration is a set that covers the items that are there in that configuration. So this is an LP formulation for this problem, which looks very similar to a set cover LP. So here the variable xc is 1 if we pack the configuration C and 0 otherwise. Okay. So the objective value is the total number of configurations that we use and the constraints that we have that so here we sum over all configurations that contain an item I, and the sum of all of those should be greater than or equal to 1, which means that item I is packed. Okay. And if you notice that the total number of configurations can actually be exponential. So this linear program has an exponential number of variables, but it's still possible to get an approximate sparse solution to this linear program in polynomial time. Okay. And solving the linear program is a different problem altogether. In fact, uh, we worked on this problem and those are like separate papers. Yeah, I mean, just subset, but for the geometric bin packing case, it also means that in addition, we also look at how can we pack those items into the bin. It also captures the position of the items in the bins. Okay. 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 So how do we round the configuration LP? We randomly. So the configuration LP's optimal solution need not be integral. So some of these variables can have values strictly between 0 and 1. So we randomly round it, which means that we flipped a biased coin, and if it is heads, then we set its value to 1. Otherwise, we set its value to 0. And we select the biases of the coins in such a way such that the expected value of the objected value does not increase too much. Okay? But after this rounding, the LP need not be feasible. Okay? So which means that some of the items will get packed and some of the items will remain unpacked. So the items that remain unpacked, we pack them using a known bin packing algorithm. So this is how we're combining linear programming with another bin packing algorithm. Okay. So this is what the round and approx framework is like. We can think of it as a meta algorithm. It takes as input an approximation algorithm for bin packing and an approximation algorithm for solving the configuration linear program, and it outputs another algorithm for bin packing, which has this approximation ratio, as you can see. Yeah, okay. So the round and approx framework was given by Bansal, Caprara, and Sviridenko, and when they gave this algorithm, they used the existing best algorithms to get the best known algorithms at that time. And even now, the best algorithms for vector bin packing and geometric bin packing use the round and approx framework. Okay. So now I've talked about geometric and vector bin packing, but these are not the only variants of bin packing. You can also have other variants like packing circular items into circular bins, or variants where two items don't want to be packed together and things like that. Okay. But the round and approx framework is not tailor made to geometric bin packing or vector bin packing. It can be, so it seems like a simple and powerful idea and has the potential to give good approximation algorithms for a wide variety of bin packing problems. But there is a catch that not all algorithms can fit into the round and approx framework. Okay. So the initial authors said that the algorithm should have a property called subset obliviousness, and if it satisfies that, then we can plug it into the round and approx framework. And then later Bansal and Khan showed that there's a more general class called rounding based algorithms for geometric bin packing, and those algorithms can also fit into the round and approx framework. And so now the question arises that can we generalize this even further, and that's what we do in our work. We not only generalize the framework to work for the multidimensional, for the generalized multidimensional packing problem, we also saw that some of the previously known algorithms, like the next fit decreasing height algorithm for geometric bin packing, even those kind of algorithms fit into our round and approx framework. Yeah, that's it.
Okay, so when you round your configuration LP, it has exponentially many variables, right? So how do you flip this coin for each if you want to solve it in polytime?
You mean how do we figure out
How do you round the configuration LP in polytime? Because the number of variables is exponential, and if you're tossing a coin.
Oh yeah, okay. So this is, so just like the ellipsoid algorithm has this property that even if we have an exponential number of constraints, we can still solve it if we have a separation oracle. Similarly, there are other algorithms for linear programming which, like, even if we have an exponential number of variables, there are certain, if we provide certain oracles, then we can solve the problem efficiently. So in this case, this oracle would be the corresponding knapsack problem. So in the knapsack problem, we have a set of items, and each item has a profit associated with it, and we want to pack a maximum profit subset of items into a single bin. This is the knapsack problem. So if we can efficiently solve the knapsack variant of a certain bin packing problem, then we can also solve the corresponding configuration linear program. Oh no, it's no, not using the dual. Okay, one of the first for the geometric bin packing problem, when Bansal, Caprara, and Sviridenko gave the round and approx framework, they solved the configuration LP by like solving the dual and then somehow using that to get a primal. But the later algorithms use different techniques. So there's an algorithm for linear programming by Plotkin, Schmoes, and Tardos using multiplicative weight updates. So that's a different kind of algorithm, and we use that for our purposes.
Okay, maybe we'll take other questions, if any, offline, and thank the speaker.
Okay, thank you.